Hi, my name is Johannes. I'm happy to present our paper Breaking Symmetries with Root Click and Lex Top Sort, which is joint work with Markus and Stefan from Vienna. Let's right start with the motivation. Fractional hypertruth is a combinatorial measure that renders CSP as well as sharp CSP tractable. More precisely, it makes instances solvable in time polynomial of the instance size and exponential of the fractional hypertruth. Is the most general known structural restriction that guarantees polynomial time solvability of CSP, and in particular it is more general than truth. Recent works have considered the computation of the measure, and one approach formulates an SMT encoding, so satisfiability modular theories, that determines the width and provides a practical implementation called FRA-SMT. Another approach implements a combinatorial algorithm into a solver called triangulator, and a latest version called triangulator MSC. The solver is quite successful in many hypergraphs and solves most of the instances quite fast. The success of triangulator drove us to the question whether one can improve the SMT approach further. A classical approach for combinatorial solving is then to use symmetry breaking. And that is the focus of this paper. Why can symmetry breaking be particularly interesting? Fractional hypertruth is defined in terms of an unrooted decomposition tree. The core of the SMT-based encoding is an ordering-based characterization of fractional hypertruth. A hypergraph with n vertices has n factorial linear elimination orderings, and many correspond to the same decomposition tree. In consequence, it seems obvious that there is much room for symmetry breaking strategies. Then our immediate research questions are: can we apply symmetry breaking to the SMT-based approach for finding fractional hypertruth decompositions and hence the fractional hypertruth? Are there different versions of symmetry breaking techniques possible, and what are the potential effects? For example, if we have a static symmetry breaking technique that is pre-computed in the beginning, or a dynamic one that is part of the encoding. Before I go into the details, let me quickly summarize our contributions. We speed up the SMT approach for finding optimal fractional hypertruth decompositions. We introduce and study two new symmetry breaking methods, and overall we investigate a dynamic and a static version of root click and top sort. I'll explain in a bit what this actually means.
The popular method in large-scale optimization, which in every iteration optimizes the problem over a subset of variables, keeping the remaining variables constant. Unfortunately, the fixed points of this method can be arbitrarily far from global optima, even for convex problems, and the class of problems for which BCD provably converges to global optima is currently quite narrow. Yet, BCD methods, known as convex message passing, are state-of-the-art for approximately solving the LP relaxation of the map inference problem in computer vision, which is also known as the weighted CSP. Their fixed points may not be global optima, but they are characterized by certain local consistency conditions, namely different forms of arc consistency. Focusing on linear programs, we are going to show that fixed points of BCD are identical to fixed points of another method called primal dual approach, which can provide upper bounds on optimal value of a linear program. It uses constraint propagation to detect infeasibility of complementary slackness conditions in a primal dual loop to iteratively improve a dual solution. This approach is related to the primal dual method in linear programming, and we propose it in our second submission as a generalization of the virtual arc consistency algorithm. In detail, we proposed to replace enforcing arc consistency by general constraint propagation in a system of linear inequalities. Though this is not a BCD method, the fixed points of this approach are also characterized by arc consistency of the active tuples. We show that the primal dual approach with a specific kind of constraint propagation and BCD have identical fixed points, which unfortunately may not be optima, but only provide an upper bound on the optimal value. We precisely define the propagation rule and show that its properties resemble other already known propagators, such as arc consistency closure propagator. Consequently, BCD on any LP in any form with any blocks of variables in fact implicitly performs the proposed propagation rule. Using these results, the question if a given linear program is exactly solvable by BCD can be translated into the question if feasibility of a certain system of linear inequalities is decidable by a precisely defined propagation rule. Thus, the results characterize the classes of LPs optimally solvable by BCD by tools of constraint programming and also characterize the types of local minima in BCD by local consistency conditions. We will now describe both methods in detail on a linear program in general form and then state our results formally.
Hello, and welcome to my presentation on quantum accelerated global constraint filtering. My name is Kyle Booth, and this is joint work with Brian O'Gorman, Jeffrey Marshall, Stuart Hadfield, and Eleanor Riffle. This work is motivated by recent advances in gate model quantum computation. So gate model quantum computers are universal processors, and unlike special purpose processors such as quantum annealers, are capable of implementing any algorithm that can be expressed as a series of quantum logic gates. Research in using gate model quantum computation for accelerating classical algorithms in search and optimization has actually seen a flurry of activity in the literature, with recent contributions for the simplex method, backtracking tree search, and branch and bound. So our group became curious to know and investigate if we could use gate model quantum computation to accelerate constraint programming. In this work, we propose a quantum accelerated filtering algorithm for the all different global constraint. Our algorithm follows the classical algorithm for domain consistency, however it accelerates the various subroutines leveraging existing quantum algorithms for graph problems. Our algorithm improves over the classical worst case complexity by a factor illustrated by this expression here, where the cardinality of x is the number of variables and the cardinality of v is the number of unique domain values. We also extend our results for the all different global constraint to filtering of the global cardinality constraint, showing an equivalent improvement in worst case complexity. Lastly, we investigate the use of quantum filtering within a classically managed backtracking search and comment on some of the issues in doing this. I want to note that the algorithms in this presentation require fault-tolerant quantum computers beyond what is currently available and thus cannot be immediately implemented. We believe that quantum global constraint filtering is attractive for the CP community, as quantum computing can theoretically, as we will show in this presentation, offer significant speedups. We also believe that this concept is quite attractive for the quantum community because constraint programming, the paradigm of CP, provides a structured way to carve off portions of complex problems that can then be worked on by a quantum coprocessor. Filtering subproblems, just by their nature, require fewer qubits than to solve the entire global problem, and so these filtering subproblems become feasible on earlier, smaller quantum coprocessors. If we look at this figure at the bottom here, what we envision is having a classically managed backtracking tree search. So we have a classical processor managing the backtracking tree search, and then at each node we can accelerate global constraint filtering with a quantum coprocessor that solves a variety of quantum subroutines that allow us to do that quantum global constraint filtering faster.
Hello everyone, my name is Ian Howell and I will be presenting a talk on our paper, Visualizations to Summarize Search Behavior. Currently, the only sound and complete method for solving a constraint satisfaction problem is to use backtrack search, but backtrack search invariably suffers from thrashing. To reduce thrashing, it is industry practice to enforce a given consistency property. This comes at a trade-off because the property takes time to enforce. The trade-off of running a higher level consistency, higher than generalized arc consistency that is poorly understood. Finally, past works have focused on metrics calculated at the end of search, but in this paper we propose to summarize the search process as a whole instead. So our contributions in this work include a criteria for computing the distance between two time samples based on the backtrack per depth metric proposed by Woodward et al. We then use this distance metric to cluster the samples taken during the search process, and we create a history of qualitatively distinct regimes or time intervals. Finally, we present a new visualization that examines the behavior of variable ordering heuristics. Our distance metric is based on the Kullback-Leibler divergence, or KL divergence, and aims to capture the change in the shape of the BPD. We then use this metric to perform agglomerative hierarchical clustering. We start with the samples, and then we successively build up a clustering tree and then cut the tree at a user-defined detail level. We are able to use this summarization process to find a structural issue in the MUG 125.3 benchmark instance. We further propose a visualization of the variable ordering by looking at the number of instantiations of each variable at each depth. We do so in a heat map where we have on the x-axis the depth of the search tree and on the y-axis the variables of the instance. To order the variables in the instance, we calculate a weighted depth and order the variables accordingly. This helps us to explain why DOM-DEG can do better on another benchmark instance, as opposed to DOM-WDEG, which usually performs the best. In our talk, we show how the summarizations can be used to explain the changing behavior of search, the use cases for researchers and developers to study the impacts of specific strategies, and how the summarizations can catch small and large behavior that a human cannot be expected to. So come view our talk if that sounds interesting to you. Thank you.
Hello, my paper is about finding an efficient set encoding for the Hamiltonian cycle problem. The Hamiltonian cycle problem, HCP in short, is one of the well-known NP-complete problems. Given a graph, directed or undirected, the goal of the problem is to find a cycle in the graph that includes each and every vertex exactly once. Since HCP occurs in many combinatorial problems, CP systems provide a global constraint named circuit for the problem. Given a graph G represented by a list of domain variables, an assignment of these variables satisfies this constraint if the assignment represents a Hamiltonian cycle. So for example, for this graph, this assignment 2, 4, 1, 3 satisfies the constraint. However, the assignment 2, 1, 4, 3 does not satisfy the constraint because this subgraph contains two subcycles. We begin with Minizinck's decomposer, which uses a position variable for each vertex. The generated constraints ensure that all the problem variables are distinct, all the position variables are distinct, and the positions are connected into one cycle. This encoding does not perform well. It can only solve the nice tool problem for size 8. The Int'l IP model is well known for HCP. It uses a matrix of Boolean variables H. Hij equals 1 if the arc ij is in the cycle. It uses degree constraints to ensure that each vertex has exactly one incoming and exactly one outgoing arc. It uses subcycle elimination constraints to ensure that, in each subset S, there is no subcycle in the subset. However, This encoding requires an exponential number of closes to encode. There are several n-cube encodings which deal with position variables in different ways. However, these encodings suffer from code explosion problems, and they are unable to encode the nice tool problem for large sizes. Recently, Andrew Johnson proposed an encoding called LFSR encoding, which is very compact, uses log encoding for position variables, and uses linear feedback shift register to generate the next position. This encoding is able to solve the nice tool problem for size 22, but does not scale well.